Hello there.
Folks, welcome back. We are doing exponential modeling. You may have heard of that word exponential used frequently. Many times that word is used incorrectly. We will show you what it means to grow exponentially. Of course, it has something to do with the idea of an exponent. Please note that there are these pages in the textbook that you can look to. I have not done any examples from there, so if you are needing more examples, may I suggest that you go ahead and seek out those pages for some more information. Okay, we'll present a basic exponential model. We're going to show you a few exponential models in this class, but we're going to start you off with a very basic one, the fundamental one. Here is an exponential model. For those of you wondering, a model is an equation or a set of equations or inequalities or an expression that mathematically explains what you see in reality. All right. So in our case, we're going to focus on populations. So populations of people, populations of animals, of bacteria. Their growth can be modeled by mathematics. Here is one such model. All right. For those of you a little rusty on this is of course the function notation. This takes an input of x and it gives you an output value. We have three variables here and the x. What's important to note about exponential modeling is that the variable is the exponent, okay, or the exponent is the variable. Make sure you write that down somewhere, very important. The exponent is the variable. Notice the exponent is the variable. So in this case, b is going to be our growth rate. Now, what I mean by growth rate is how fast does something populate or reproduce. A will be a number that is affected by the growth rate. So in a population of humans, for example, there are so many humans that would be able to reproduce, right? And they would reproduce at a certain rate. Now, in that population, there's also a group of people that may not be able to reproduce. We will do problem one in class. You've all taken biology. An amoeba is a sarcodine. It has little pseudopods with which it grabs food, moves around, and at some point, an amoeba gets big enough that it goes through a process called fission. It divides, it replicates. Now, an amoeba is a great example of an organism that follows exponential growth because an amoeba doesn't really need much to be able to do what it does. So we have one amoeba, which is very important, and I want to remind you of the model. Recall that B is the growth rate. We have one amoeba that divides into two amoebas every hour. So the growth rate in this problem is going to be 2. We have only one amoeba. That's our A value. And there are no other amoebas in this situation. And so this is all we're left with. We are talking about time. So I'm going to change the x to a t. And we would have 1 times 2 to the t power. Again, there is no c in this situation. Now, what we would do is we would go ahead and replace t, in this case, with a 5. Some of you thinking, okay, Mr. You're doing way too much because I could just draw all these amoeba, and after I count all the amoeba, I have 32 amoeba. And I'm like, good job. But what happens when we get to part B when there's more than 32 amoeba, right? When we have hundreds of amoeba. So we're starting you off with a simple example to help you understand the idea. If we put this in the calculator, we end up with 32 amoeba. The idea is understanding how to set up the model. The model is an equation that models the growth in this case. So in our next situation, we have 2 amoeba this time. So instead of there being just 1, there's going to be 2. And the growth rate is different now. It's 3 amoeba every hour. And I want to know what happens after 5 hours. Now, so far for A and B, we did not have a C value. The problem only stated that we had amoebas that were dividing. In part C, we have a mixture of amoeba.
Hello there.
We have 3 non-dividing amoeba and 5 other amoebas that do divide. This is our A, this is our C, and the dividing amoeba divide into 2 every hour. So I have 5 with a growth rate of 2 plus 3 that are not reproducing. They're not dividing. We're looking at 7 hours. If we put that in a calculator, you're going to get 643. So we're entering a part of mathematics where there is quite a bit of word problems, and it is very much real life applicable. I don't have to make up stuff. What we've been talking about so far is something like this, right? 2 to the x power, where the exponent is the variable. I need you to take a moment to reflect on how does 2 to the x differ or compare to x squared, which you've been taught in Algebra 1 and Algebra 2. And then my question to you is, which one grows faster? You may wish to explore this using Desmos. Problem 3. Let's talk about a more advanced exponential model for more advanced populations. So we're talking about living organisms that are growing at a constant growth rate of r. We will show you this model right here. N is pretty much like our f of x from the last model that we showed you. N naught would be the initial population, the population that is growing, right? And in this case, we actually have something very special going on, a built-in growth rate right there, E. E is, in some books, it's called a Napier constant. It's a number similar to pi, but we also have, in the exponent itself, we have this growth rate R, which will be an actual population's growth rate as a percentage, which we would then convert to a decimal. In this case, why must R be greater than 0? What happens if R is 0? What happens if R is less than 0? So looking at the model itself, don't write this down, just watch for now. R is the thing in question. So if I were to make R 0, anything to the 0, this would be 0 times C would be 0. And anything to the 0 power becomes 1. And what happens is that we end up with n is equal to n naught, meaning that the population is equal to the initial population. So if R is 0, here's where we can start writing things down. If R is 0, then the population is not reproducing. Now, if R were to be negative, right? Well, that's not a good thing, because if R is negative, it's not reproducing, it's actually dying off. It's going extinct. Okay, we call this in the math world decay, but in reality, it's just death and extinction. But this is not a both at the same time. Okay, this model only tells us if a population is growing or if it's decreasing, if it's decaying. It doesn't do both at the same time. So there's a limit to that. Why must R be greater than 0 if I want growth rate? Because that makes it positive, right? And if it's positive, then we do have a population growth. Now that's for this model. We will revisit the other model from before, the other exponential model, the basic one, and show you how the growth rate is affected there. How can this simple model be used to predict the Earth's human, the Earth's human population? This is the basic model, right? Well, not the basic model. This is the more advanced model that we're using right now for this problem. Population at any given time depends on the initial population. So we must pick a beginning population and a beginning year. So if we make, for example, 2020 be our initial population, or 2021, for example, be our initial population, then that's going to go in this spot right here. If we were to use a look at the world population clock, we will note that it's about 7.8 times 10 to the 9 people living on the earth right now. The E is built in. That E is going to be there. The human population growth rate in 2020 was 1.05%. However, we don't put the decimals. We don't put the percents. We put the decimals. So it'll be 0.0105 times t. And that should probably clean this up a bit because it's a function of time. So from this point, this is using 2020 numbers, right? If I want to find out based on this model and this human growth rate, and of course, when I talk about human growth rate, I'm talking about this population percentage right now. Um, we could model using this equation how many people there'll be on the earth in 20 years or 30 years or 100 years. Back in 2017, the human population growth rate was 1.12%. In 2018, it was 1.10%. In 2019, it was 1.08%. And in 2020, it is what was 1.05%. Um, I've been teaching this for a while. The human population growth rate for the world has been decreasing. Even though this initial population, right, has slowly crept up over the 15 years that I've been teaching, the growth rate is going down. And these are just facts. These are just numbers. So it's up to you to decide what that means for the future of the human race. What are the limitations on this model? This model, like I mentioned earlier, right, is either growth or decay. Now, when I mean decay, I mean extinction, death, that kind of a thing. So it doesn't model both at the same time. Now, there is, of course, a human population death rate, but it is overpowered by the growth rate. And so the number that we actually presented to you, the 1.05%, takes both of them into account. So we're technically cheating the mathematical model by using that number. Okay, so it's not too bad of a model, but there are limitations, of course. So we don't get to actually follow both growth and decay technically at the same time. It's either one or the other one. That we have infinite lives, unlimited resources, unlimited space, unlimited shelter, right? Eternal reproduction, those kinds of things, okay, which are not technically realistic. This model does help in some aspects. It does help with a certain population growth for a short amount of time. It does help in predicting the future. A model like this can be used to predict pandemic outbreaks, COVID-19. It can be used to predict acreage burned because of wildfires. So don't throw this model completely away because it has restrictions. If we're dealing with entities or quantities or things that um, don't necessarily have a shelf life, then this model works really well. Or if we're modeling just a few days, weeks, or months, it works out pretty well.
Goodbye.